poorly timed server migration, which took one of the main data sets offline for about 24 hours and caused me to have a huge panic. So as I say, these notebooks are available on the hub. You're welcome to follow along, though I would appreciate it if you didn't all run the notebooks at exactly the same time, because I would hate to DDoS one of the servers that we're going to use for access. So by all means, follow along at home, but maybe don't run all the notebooks at once. Who am I? This is a talk originally given by Felipe Fernandez 2 years ago. I have modified it somewhat, but basically all the original material is his, so all credit to Felipe for making this. I see he's actually on this Zoom call, so we have the best person here to correct me if I'm misrepresenting any of this. But me and Felipe have a very similar job role, being physical oceanographers and sort of data scientists, code janitors. I think we both spend probably more time on GitHub than we ever have on research vessels at this point. And we're both heavily involved in ERDAP. So this is Felipe's original slide. He's with Sakura, I believe, which is part of the kind of IUSE data system. These various groups that feed data upwards into IUSE data systems. I work for an organization called VOTO, or Voice of the Ocean. I don't know how recognizable this silhouette is on the other side of the Atlantic, but this is a nation of Sweden, between the Baltic Sea and the North Sea. We run a fleet of autonomous gliders out in the Baltic and various sort of data services from those, including ERDAP. So we might use some of our data later on in this presentation. But yeah, I finished my PhD in oceanography a couple of years ago. I attended OceanHackWeek 2021, I believe, which was fully online, from a horrendous time difference in the UK, but really enjoyed it. So this is my first time presenting at OceanHackWeek. And yeah, I hope this is informative. I would say please shout out questions at any time. I appreciate I have a slightly odd British accent and a tendency to rush. So if I'm not making sense, please stop me. Now, on to the presentation. So data. There are a lot of places to get it and a lot of methods for acquiring it. So we've got a few of the sort of major data set methods here. These include protocols like OpenDAP, servers like ERDAP and Threads. You'll still find unsecured FTP servers out in the wild. You may have to navigate those. S3 buckets, HTTPS. There are a lot of ways to get data, and we're not going to cover all of them today, but I hope to give an overview of the ones that are most commonly used within the oceanographic community. And a quick request for feedback included from Felipe's original talk. As we go through this tutorial, try to think which parts of it were useful, which parts of it less so, and we can use that feedback to improve it next time. Specifically, what are the blind spots that you want explored more? Is it more using metadata to find and explore data sets? The kind of nitty-gritty of software of how we download, slice, and aggregate data sets, though I think you're getting an XRA tutorial, possibly from Rich after this, which I think will cover a lot more of that. Finding new data sources, I've included a lot of examples. We may not have time to go through all of them in the notebooks, but if you're just looking for places to pull data, look at some of the later on notebooks in this directory and you'll find a lot of sources there. Or if you knew all of this already, I don't know, just take this as a great opportunity to relax and recover after your project planning. This will be a quick overview of the different kinds of servers and the different services that they provide. So one of the popular ones is by the OGC, which is the Open Geospatial Consortium. It provides sort of XML or CSV data, so sort of flat tabular data. It tends to be very metadata rich, and this works well for simple time series data. Think buoys, static weather stations, things like this, where you can just consider it a point with a time series of data running through it. Slightly more complex, we have OpenDAP, which is you'll primarily encounter for gridded data. So this is very popular for serving models, satellite data sets, and this will always come as binary data from a two-dimensional or higher dimensional grid. And then slightly more specific kind of data is raster images from UGC WMS. So you'll get these with any kind of tile viewer. If you've just been scrolling around on Google Maps or various slippy maps, that's the sort of thing that's in the background. So you might get like a satellite data overlay. Maybe you're using like a sea ice data overlay for piloting your instruments. You're getting like a chlorophyll overlay just to see where hotspots are popping up. So you don't tend to get like what we might call scientific data. It's more for quick visual interpretation, but it's really useful for integrating into web apps, things like this. And then finally, ERDAP, which has a RESTful API. There's a little asterisk for the response that ERDAP gives, because ERDAP can give you basically any data type or data structure that you might like. So that's probably the dominant method of serving oceanographic data these days. So we're going to spend a bit more time on ERDAP than we are on the other ones, not least because unlike these other protocols, I actually kind of understand ERDAP. Do not ask me how WMS is working under the hood. I will not be able to help. So what are we going to see in this tutorial? As I said, we're going to browse and access data from a variety of servers, including ERDAP, OpenDAP, Survey, WMS, and CSW and CCAN. So these are more sort of like data aggregation services that we'll get onto more at the end. These first examples are quite well fleshed out. The last ones are a bit of a whistle-stop tour. There are some links here to the IUS Code Lab where there are much more detailed examples of these. No. Section 1, ERDAP. So we're going to explore an ERDAP data server with the Python package erdapy, written by Felipe. I don't think he put that in his original presentation, but I can say it. And we're going to find data from a specified time and region. Then we're going to download that data, do some slicing and some plotting, and kind of just give like a fully reproducible workflow for how you would go from looking for that data to using it on your computer. So what is ERDAP? So ERDAP is a server that anyone can deploy. So there are something like 100 or so ERDAP servers in the wild. They're all running for the basic ERDAP software, which is written in Java. And the main goal of ERDAP is to provide flexible outputs. So it's like HTML tables, CSV files, binaries, pretty well-structured NetCDF files, and lots of well-structured metadata, which helps with discoverability. And it uses what's called a RESTful API. The best way to think about this is that every request to an ERDAP server is a URL, and that URL will always get you back the same result. So that as compared to some other services that might require a sort of shopping basket style interface where you have to click various buttons or go through logins, the idea with ERDAP is that you just have to craft the right URL and then you'll get the right response back, which is nice because it means it's very easy to program against. So erdapy is a Python library which just creates those URLs for you, and there are other programming languages that have implemented this, such as RERDAP and others. And ERDAP does some standardizing. The most important thing it does is standardize dates. One thing that I've come to realize, having kind of made the transition from being an oceanographer to being a data scientist, is like a far larger chunk of my time than I would like is dedicated to dealing with date time. I think I spend more time searching convert X date time into Y date time than I would ever like to admit. So it's really nice that ERDAP standardizes date time. And ERDAP also does server-side searching and slicing, which means that it will, as well as having search functions on the ERDAP, it will subset large data sets for you. So if, for instance, you've got a huge model reanalysis that might occupy terabytes, rather than you having to download the whole thing and then just extract that one point in the middle of the Atlantic and maybe 10 years of data that you're interested in, you can send a well-formulated request to ERDAP. It does all the heavy lifting and sends you only the data you need, which is great if you're bandwidth limited or storage limited. Like the ERDAP server almost certainly has better processing capabilities than your laptop. So much for what ERDAP is. Let's see what ERDAP does. So in this first cell, we're just importing capital erdap from the erdapy library. We specify a server, in this case, the Ocean Observatory server, and a protocol. erdap has two kinds of data: table dap, which is anything that you can imagine being like a flat Excel spreadsheet of data, and grid app, which is more for model data. We're going to start with table dap as it's a little simpler. So first, we're going to just ask the server what services are available. So we write this little query to the server, and it tells us, okay, there's... Hello, yes.
Can you make it bigger so we can't really see the code cells?
Ah, hang on, let me try that. Is that any better?
Yeah, thank you.
Grand, thank you for the intervention. Yeah, so this server is telling us we've got several hundred table dap server data sets. And let's see, say we know that we just want practical salinity. So we can use the standard name, seawater practical salinity, and we use this categorize by keyword, the server. And the server says, okay, looking for data sets that only have practical salinity, that's about 400 data sets. We can then be a bit more strict. So say we have a search box of interest, which we just specified with these longitude and latitude. This code cell is not so important. I'm just making a map, which is not rendering very happily. Sorry, I think the zoom mode messed it up. Let me go back a slide. So the map that we're making is just a box off the northeast coast of the US. We can skip the rendering of that. But the important thing is we give the erdap this data. So we're giving it a time extent, a geographical extent, and a standard name, and we'll see what data sets it sends back. So this time it says, okay, it's got 38 data sets that fall within this box. And then, sorry, it's struggling a bit with Zoom on that. But we combine those arguments, hand them to erdapy, and we get it to print a download URL for us. And I just want to dwell on this moment. So we can just click that URL and it will download the data for us. But what is in an erdap URL? Because this is really the core of what erdap is and how it works. So all of libraries we use to interact with erdap are just about building these URLs. This is what makes it a REST service. So the root of the URL is the URL of the website itself. We then specify the protocol. As I said, that could be table dap or grid app. We give it a dataset ID, a requested format. So if that's .html, it goes back the HTML web page. If it's .csv, it goes to CSV file, .nc, .mat, etc. We can then give it a list of variables and a little dictionary of bounds for server-side slicing, so that we can tell it that we only want the data that fits within a certain bounding box. So this seems a little complex and maybe a little unwieldy at first, compared to like a nice interface where you sort of drag and drop on a map and select your data sets. But the real advantage of this is it allows you to make programmatic queries. For instance, if there are 100 different data sets that you're interested in, rather than having to go and fetch them each individually, you could just write a quick for loop that makes this URL and just changes the dataset ID each time. Or if your zone of interest changes, you could rerun your whole analysis just by changing the longitude and latitude extent if you want to extract data from a different box. So that's why we have this approach. So it took a while to get here, but eventually to pull the data after we've constructed our URL is just a case of calling the to pandas functionality from erdapy. So pandas will, in the background, make a call to erdap to pull that CSV. and then pass the time and then write it out into a data frame. Pandas is nice if we're dealing with tabular data, as it's a quick way to interact with the data. Alternatively, we could have used the toXArray method, which pulls the netCDF instead. So here is left as an exercise for the reader to think when you would prefer to xArray versus to pandas to get your data and what you will do with it. But both methods are valid on TableDAP area. So we have our data set, and now we want to just make a little plot. So just using some standards, sort of pandas subsetting, and making a quick matplotlib plot. So this shows, I think, surface salinity. Yes. Yeah, doing a plot of surface salinity.
Callum, are these the salinity and the temperature, the average for that box?
Great question. So, no, this is a subset of data from one of the instruments that's recording within this box. So when we do these querying commands, what we're asking ERDAP is to give us a list of data sets that have data within this box, and then to send all data within this box. So you can see this comes from what looks like a static platform at this longitude and this latitude, and this is just a time series of data from it. So if this is a buoy, for instance, we'll get the whole time series from that static buoy. If it's a glider that's crossing into the box and out of the box, we'll just get back the data that's within that box, but we haven't performed any kind of averaging on it, though we can do, and I think we'll do some of that in a later slide. So yes, thank you, good question.
Each line is a data point from one instrument that happened to fall within this box.
Exactly, yes. So we've just kind of simplified this as a plot through time, but this instrument may also be moving through space. It's kind of a constant problem with glider data. And this is just another plot where we've made a little tensile scatter. I've hidden the code during this presentation, but you can check that out if you want, just to show this kind of classic near shore sort of TS plot. This is very constrained, though it looks like maybe someone hasn't run their quality control on this, because these big excursions probably aren't real. But we'll cover a bit of QC later. So as I said, you get a lot of different responses from ERDAP. So what we're doing here is we're just setting a few different responses, like MATLAB files, JSON, NCCF headers, and we're getting it to generate the URL each time. So you could click on these links and it would download that file. So this just kind of illustrating what I said before about the nice thing about having a RESTful API is you can just iterate over that URL and change things to get replicable results. It also means that once you've crafted your URL, you can just send the URL to a colleague. So rather than having to figure out how to Dropbox someone like 20 gigabytes of model reanalysis, if you've crafted the right URL, you can just send them that. And it makes that reproducible analysis much easier. So yeah, there's a little exercise here. If you want to dive into this a bit more, I've linked to the Ocean Observatories ERDAP, the IUS Glider DAC, and the Voto Glider server that I run. So yeah, I would encourage just finding a data set of interest, downloading it in a format that you're familiar with, and plotting it. Even if you're more of like an R programmer or a MATLAB user, I hope you, with the tools that you've got, you can at least run this script, just replace the server with the server you're interested in, download the data, and then plot it in whatever tools you feel more comfortable with. All right, so that was ERDAP. We're gonna come back and spend some more time on that if we can, but next we're gonna go through some other servers. Before I do, are there any more questions on the ERDAP server or the demo we just did? Great, I'll move on. So OpenDAP stands for Open Source Project for a Network Data Access Protocol, is actually one of the less torturous acronyms that I've encountered in this space. And it provides access to metadata and data subsets without downloading an entire data set. So you might think that sounds quite familiar to what ERDAP is doing, which is correct. Like ERDAP is built on the OpenDAP protocol. And many tools that can read netcdf files can talk to OpenDAP URLs directly. So I think Xarray can do this, and you'll often get something like a thread server sat on top of Xarray. The nice thing about using something like Xarray instead of just raw requests to it is that Xarray has sort of CF standard names. You saw how earlier we searched for the CF standard name for seawater practical salinity. So it means that rather than having to try and guess what variable name someone has used in their data set, you can use these commonly accepted CF standards, and it takes a lot of that trial and error out of it. So the learning objective of this, we're going to get some ocean model data from threads with an OpenDAP query and discuss the differences between that and ERDAPI, and then do a little bit of plotting. So accessing one of these servers is as simple as finding the URL to one. So we're going to use Xarray for this. And as I said, we also are going to use CF Xarray. We just import it, and then in the background, it will do all of this translation and standardization for us, which is nice. So we get the URL to notice this is a thread server. We get the URL to a data set, and we have Xarray open that data set. Now, just taking a look at it, we can see the axes of this. And so this is a multi-dimensional grid with X, Y, Z, and time. You see there are even multiple time axes, various cell coordinates, and you can find the standard names for the different variables here. So we've got velocities, temperature and salinity. I found a very standard oceanographic data set, but it's on this multi-dimensional grid, which means that it's probably going to be a very large data set. So we don't want to download the whole thing. So rather than downloading the whole thing, we tell the OpenDAP server what variable we need. Again, so this time we're going to go for seawater potential temperature. Notice we're using these CF standard names to avoid confusion. We give it a time and a depth level to operate on. So in this case, this is a model where Z is defined positive up. So if we want the surface level, we want the last level, which in Python language is the -1 index. So we do a selection of this where we say, okay, go to the data set, take this variable, do a selection at the date, and then do an ICEL where the density level is that last density level. And then we'll just import matplotlib and do a plot of this. So we get a nice kind of surface plot of the extent of this model showing the seawater temperature at the surface. And we can see that it's being averaged in time because we just wanted a 2D plot here. So there is quite a bit going on in this Xarray. We're doing the selection and the ICEL to slice up this data set. I just want to say that all of that is being done on the request. We're not downloading any of this data. It's being subset on the thread server through the magic of Xarray. But I think I'll leave that to Rich to explore more later, not least because I have to check the documentation every time I do any kind of Xarray slicing. That's how we get our data set. So as to how this compares to ERDAP, we have the similar power of server-side subsetting, a similar approach to sort of lazy evaluation. So the idea is that you don't request the data set until you have to. So you do the maximal amount of slicing and subsetting on the server side. I would say one of the major differences with OpenDAP is that I think it only serves NetCDF or only serves binary. So it works very well for gridded data, but for time series, you don't get this flexibility of returning like a CSV file or an HTML file. But in terms of gridded data, they perform very similarly, which makes sense because ERDAP is using OpenDAP under the hood. So yeah, I think that's it for OpenDAP. Are there any questions on that? No? Nice. On to Survey then. Now I'm getting really out of my depth. So I hope if there are questions on Survey, Felipe will jump in and help me with them. But Survey is a way to access old school SOS datasets via an ERDAP server. So it lets us get COOPS data or co-ops data. So what are these co-ops data? I think these are American terrestrial and oceanographic data centers. And the interesting thing about these is they use the NWS or National Weather Service ID points. So you can make a request to COOPS with, again, a geometry where we have a sort of longitude and latitude extent, and it gives us the name of all of these. So this is useful if you're dealing with, I don't know, an ocean professional, like a fish person who may know the name of their local weather station, like Fernandina Beach or Fort Myers, and won't necessarily know the code. So this is a very useful way to make those connections to kind of more real world data examples. So if we know that we want some data from the duck station, we can just make a request for that in the name column. So find the duck looks to be in North Carolina, and it's a point which I think is a tide gauge. So if we set that station and we look for the water level data, and if here I've just been searching over the last 15 days, I can then do a quick plot of the tide gauge data at that point. And again, you will see that a lot of this is sort of a similar format. When we make these requests, we give it a start time, we give it an end time. When we did the search earlier, we were giving it this bounding box. So we're probably seeing a pattern emerge with a lot of these servers is that just because of the volume of data, we're encouraging people to only request the data they need by subsetting this, which means that downloads are easier. You're not being inundated with data you can't use, and it's easier for the server maintainer as well. So if I would say one thing, before you run a query, just try and get the data that you need. And yeah, it saves everyone a bit of time. And so this is using ERDAP under the hood. The next one that we're going to rattle through is WMS. So the Web Map Service. Like I said, this is the service underneath a lot of Slippy maps. It's serving PNGs or GeoTIFFs, and it allows you to add cool little layers to your application. So we're going to use the IPy leaflet map. So leaflet is one of the most common JavaScript libraries for showing simple Slippy maps, and we're going to pull some hurricane data. So what we're doing here is we're just setting some times for the slider. And when we're going to make our map. So what we need for these servers is, again, similar to ERDAP, you break this, you're kind of breaking the request down. You've got the URL to the server, you've got the layer that you want, and a time slice, and what format you want the image in. And we make a little base map, and let's see if it will render this time. Okay, that seems a little happier. So this is, I think, some data of a hurricane heading towards Houston. Not the most recent one. I probably could have updated that, but from one from back in 2022. And you should get a nice little slider, which, if it works, will slide it through time. Sorry, I think rendering this presentation into slides has broken the slider, but if you run the notebook, you'll be able to get that functionality. So I find these WMS servers really useful. We use it to load live ice maps into our piloting application for our gliders. So we try not to send them under ice shelves without meaning to. Say not so much for scientific data, but for visualization, they're really handy. And there's sort of getting WMS data is a pretty simple request. And then we get onto catalog service webs. So this is the question of where does the data come from and how do we find the data? Very often I'm asked, like, what is the canonical origin for this data? Is there a kind of server of servers or like one master data server to rule them all? Generally, the answer is no. A lot of time you have to just kind of trawl various servers to find the data you want, which is often the hardest part. Like I've showed you how to craft search URLs against a specific server, but finding the server you need is kind of tricky. But there are a couple of things that have this capability. So one is the iUse CSW server, and the other one is PangeoForge. So this catalog service for the web is a single source of finding endpoints, and you can filter against those endpoints to be directed to the server that you need. So what it looks like is this. So on the left-hand side, you have a bunch of different data servers. Maybe they're running ERDAP, maybe they're running threads, maybe they're running something else. And then you have this catalog server, which harvests these data, transforms them into a common standard, and then publishes them all out through some magic of geoportals into what's called the iUse catalog. And the whole idea here is to enhance sort of dataset discovery and use of metadata. So it's not that all of the data themselves are being hoovered up. This would be impractical and a duplication of effort. It's just we're looking for metadata. So that when someone searches the iUse catalog for, I don't know, surface salinity in the Gulf of Maine, they get sent to the server that can provide them with that data. Now, this is the kind of thing that sounds quite easy when you first describe it, but it's actually really difficult to manage because everyone has different ways of using their metadata. Like we still haven't really agreed on a single way to call sea surface salinity. There's the CF name, but not everyone uses it. Not everyone's putting it in the same field. Maybe those files aren't always compatible. But this is the closest thing we have to this sort of server of servers, I'd say, is this iUse catalog. If you're interested in the iUse catalog, there is a lot more examples on the iUse Code Lab, which I've referenced before, but I've just linked to again here. And there are some other sources of data here, which I've added. So if you like the way that the ERDAP worked, there's a curated list of ERDAP servers. There's also a multiple ERDAP search, which let's try live now. I'm feeling lucky. So this is another data aggregator, which actually so you see it searches those 61 ERDAPs. What shall I search for? I'm not very original. Let's look at glider data. All right, it's found some of mine. That's good. If I hadn't, that'd be embarrassing. Who else? Who else has got glider data? It's me. That's eModNet, physics. That's gliders at iUse. It's a lot of gliders at iUse. Pasios, PacIUse, Hawaii, Tamu. Yeah, you can do various more strict searches here. What's in main? Yeah, I really like this tool. It's quite simple. It gets back very rapid results, but it is only searching a subset of, I think it's 60 ERDAPs. In fact, it's the 61 ERDAPs from this list of ERDAP servers posted above. So if the ERDAP server is not on that list, it won't appear on erdap.com. That's a nice one to try. There's the EDS model viewer, and you can use Siphon to explore threads servers. So yeah, those are all places to look for if you're trying to find data. And here I wonder, how does this all work? How do these pieces all fit together or not, as the case may be? And the answer is standards. I wish it was more exciting, and I wish the standards were kind of better implemented than we have. Like some standards are wildly successful, like NetCDF, I think has made all of this possible. If not, it'd be even harder than it is. But as well as standards making it easier for data providers to kind of amass their data in a way that makes sense and make it searchable through something like ORDAP, using standards is also really good as a data consumer. So I'm just going to illustrate this with a couple of examples of accessing the same data set. So I've downloaded a data set in a cell I've hidden here, and I want to make a plot. So if I want to make a plot of some netcdf data, the way you might do this is to get the netcdf4 library and use the dataset function. So I open up my dataset. I then think, okay, I want to make a plot of salinity. So I open salinity. This is 4D data from a model, but I just want to make a line plot. I just want at a certain point in time, I want to give me a plot of surface salinity. So I need to do this sort of slicing. I say, all right, give me all the points in time, all the points in salinity, give me just one bit of ln, one bit of lat, and all the points in depth. And then I select time, I get rid of the -9999, which are the fill values for NaN, because this kind of netcdf doesn't support setting NaNs. I then have to convert the times into CF time. I have to do a kind of mask because I only want the data from 2021, and this data set covers like 10 years. I then finally make my plot and rotate my X-tick so it looks a little bit less trash. And okay, I finally have surface salinity for 1 year. What if instead I just used X-array? And you can get the exact same plot in a single line of code. Notice that additionally, we get the X-axis labels. And we get a little thing that says, okay, this is the depth slice 1 meter at latitude 0, longitude 0, and some nice, much more well-formatted X-ticks. Because X-array uses these well-established standards, and it has this much more explicit selection method of slicing. So I guess this is just a call to try to use standards where they're present. And if you find yourself doing a lot of manual hard coding and trying to remember which way around slices are and which order dimensions are in, there's probably a better way to do it. All right, that was it for the core notebooks. After this, I've got a bunch of more and less complicated examples. Before I dive into those, are there any questions on the material so far? Is anyone still alive out there? I'm getting anxious. Okay, fantastic. Right. So we've got a few more examples here where we're going to go a bit more into depth in getting data and what we can do with it. So if you would turn in your notebooks to page 03, combining results from multiple ORDAPs. And I really want to show this one because this is the one that caused me to lose a lot of sleep yesterday when someone had the poor grace to migrate their server farm right after I finished writing it. So in this ORDAP, we're going to show a practical example of chaining together requests to multiple servers to make a kind of combined analysis. This is a bit of a contrived example, but I think it's kind of fun. So we're going to get some OSMC animal-born data, we're going to get some Argo data, and we're going to get some satellite data. So first thing, getting all our ducks in a row, I'm just doing a bunch of imports, and I'm making a little utility function here where it will just return me a nice map of the survey area, or sorry, the area of interest. Don't worry about it. MEOPS animals. So I talked a little bit before about ORDAP search function, so I'm just going to give an example here. I know that because someone has told me that the OSMC ORDAP server has some kind of animal-born sensor data, which sounds cool. So first thing I do is I write a query against that server and I search for animal. It tells me, all right, there is one data set in the server. It's called the MEOP Animal Profiles, version 2024, seems promising, which has some animal data in it. Fantastic. So setting that as my dataset ID. Sorry, I'm just it's showing a bit too much in the cell here. I set the dataset ID to be the result of that query. I then just ask for the species, as I know that's a column, and I run a two pandas. So let's have a look at the species in this. All right, we've got sea lions, we've got seals, we've got about 4 different spellings of Weddell seal, which honestly I can relate. I never spelled that one right first time either. We've even got some turtles in here. I mean, yeah, I'm intrigued as to what HG is, the infamous mercury seal or something. So let's have a look. All right, or at least I was, an Antarctic oceanographer. So I think southern elephant seal is going to be my go-to animal. So I set that as my species. I set a slice, which is kind of around the Antarctic Peninsula. So between -90 and -60 degrees east and below 60 degrees south. I then set my variables. Just to speed up the query, I only want to get back the longitude, the latitude, the time, and the species. And I send that request to ERDAP, thinks about it for a while, and it spits this back to me. Okay, we've got 35,000 rows of data. Let's have a look at that. So we make a call to our map function, and we can see this nice slice of data from our seals. Seals are fantastic animals for surveying near coasts. They love to hang out on ice floes and on rocks, and they'll go pretty deep. These elephant seals, I think, can go down to like 1,500 meters or something. And with a little tag stuck on their heads, they're collecting data the whole time. You don't even have to pay them. It's incredible. But they don't have very good coverage out in the open ocean because there's not so much to forage out there. So if we want a more complete slice of this area, we're going to want to complement this data. So I think I already spoiled it earlier, but one program that's great for collecting data from the open ocean is Argo. So I'm going to go to another ERDAP and I'm going to get some more data. So this time I set my sights on the Ifremer ERDAP, which hosts the Argo floats dataset. I could have gone again through the previous process where I ran a search for Argo on this and got the dataset ID. The dataset ID is Argo floats. I then set my constraints. And I think this is the point where you can make it quite fun. You can set the constraints for your second query off of your first query. So we saw previously that these elephant seals have been quite industrious and they've basically filled our box. But if there was an area of ocean that they just weren't really operating in, we could just drop that from our search query so that the Argo server will only send us back data that's kind of co-located with the seals. So again, we set our variables, just longitude, latitude, time. Let's keep this request nice and light. And we get our Argo data. We've got about 2,000 rows of Argo data. So that's 2,000 kind of depth profiles of Argo, which is pretty good. Let's plot those up together. And we see the data sets complement each other really well, almost as if it was an illustrative example. We've got Argo out in the deep sea. We've got seals close to the coast. But there's still a few gaps, and we hate gaps. So if there are gaps in our analysis and we can't get observations, let's just fill it with some model data. It's probably fine. So we're going to get some reanalysis SST data from JPL. So again, I hit up my third ERDAP of the day. This one is Coastwatch ERDAP. They don't have such a good naming pattern. I'm sure it makes sense to someone at JPL, but this is what we're looking for, the JPL MUR SST41 dataset. There's a little extra line here where I make a call to GridApp initialize. There's a whole notebook on this where we talk more about GridApp, but you need to do a little bit behind the scenes with ERDAP before running a GridApp query, because ERDAP needs to know how big the grid data set is, what are the steps in space and time, so it can send the right request to ERDAP to slice it properly. But again, we're setting our constraints using data from our seals. So I'm saying only give me SST product from the earliest seal data through to the latest seal data. And I've set a time step of 365 days, just pretty arbitrarily. So we just get one slice back per year. And we only request analyze SST data. So through the magic of X-ray, we get our data set, and then we chuck it all up on a screen together. So here we've got our sea surface temperature data, our Argo floats, and our seals. This was just a little toy example, but I think it's fun to show how you can get data from multiple different data sources and pull it all together like this. And as a little bonus, if you wonder how this changes, if you want to rerun this whole analysis, including changing the geographic extent, you can just set a different animal name in that first query and everything, and that will chain through to all of the other parts of it. So if you move to some kind of tropical animal instead, and you set this, as well as, adjusting the long and lat in that first query, that query will then cascade through the other servers so that you only get back the data that you want for your analysis. So yeah, that's how we can kind of chain these together and hit our servers. But notice I did have to know that these servers existed. That's always the tricky part, is knowing where to look for the data in the first place. Once you have an NerdApp server, the tools exist to make this kind of analysis. Are there any questions on that notebook?
If we wanted to import like temperature from the Argo, we would just add it to our variables argument.
Exactly. Okay, someone did spot that I cheated here and didn't even request the temperature data. Yeah, I didn't even ask for that. I just did lat, longitude, and time. So yeah, you just need to add temperature in here. Make sure that it's the way that Argo call their temperature. I think it's capital TEMP. I don't know. Don't quote me on that. Or use ERDAP to find out what the name of temperature is. Yes. It's something I quite often do with these, is that I'll try to set up a whole pipeline just using a couple of variables or doing very small subsetting, check that it works, and then add in what I want to pull the data when I need it. All right. How are we doing for time? I think we have 10 minutes left. Should I rattle through another notebook? Sorry, I'm talking over someone.
Yeah, sorry, I was just like thinking to ask in a better format in my head. Like as a beginner, like how do you know which data sets is in the which server? Kind of like how do you look for it? Would be a realistic question.
That's a really good question, is how to find the right data sets within that server. So in this example, let's see, where's my MEOP server? One thing you can do is just go to the server itself. I realize I'm not sure I've actually showed you a NerdApp server. I think I only showed the kind of Python representation of it. But a NerdApp server is just a web page. You can click on the list of data sets, and they typically have little descriptions. I'm not sure how well that's going to show on screen, but we can see here MEOP animal profiles. So you can just take the data set ID from this column and then use that in Python, or you can use some of the methods that we showed in the first notebook. Excuse me while I scroll. Yeah, get search URL. So the search you can put in up here if you're looking for a specific variable name or you're looking for a region. There is a whole notebook on this. Notebook 5, search and filter, goes through doing this in a series of kind of more complicated steps. So first, you can just do the get search URL if you're looking for e.g. drifter data, or if you're looking for ADCP data, and it gives you back a little table of those data sets. There are then more sophisticated searches where you can send it, for instance, like a time query, like which data sets have been data in the last 6 hours. Or you can get really funky with it, like which gliders went below a certain depth within this geographical region. So yeah, I would look through that notebook 05 search and filter for sort of more ways to find data sets on ERDAP. All right. So yeah, I have, I think about another 10 minutes. What's the feeling in the room? Should I go for questions? Should I rattle through one more notebook? Should I let your brains kind of just decompress for a bit? I appreciate this is quite an intense day.
We have one vote for another notebook, Callum.
One vote for another notebook. Okay, well, that's that one voter. It's your lucky day. So of the notebooks that I have up here, we've got one using Quartod to run quality control and analysis. We've got one where we delve more into grid app. So that's how we get gridded data like model and satellite data into ERDAP. Or we have that search and filter notebook, which I just quickly bounced through. Which of those? QC, grid app, or search and filter?
I think grid app would be cooler. 2 for gridded.
2 for gridded. All right, let's roll. That sounds like enough of a majority to me. Okay, so gridded data sets. So like I said, ERDAP has a separate protocol for gridded data sets, which is called GridApp, inventively. And so I'm going to use an example here where we hit that JPL SST data set again. So the first block is the same. I set up my ERDAP server. This time I give it the protocol GridApp rather than TableDAP. Set my dataset ID, and then I run GridApp initialize. I say GridApp initialize in the background sends a request to ERDAP saying, okay, what variables does this dataset have? What grids does it have? Like which dimensions does it have? What's the spacing of those grids? What are the steps? So that stops you from sending like malformed or like invalid requests to ERDAP. Like if this is a gridded data set, which is just a satellite product, so it's longitude, latitude, and time, and you send a request which says, oh, I want the first 3 depth levels of that product, that's very embarrassing for you, and the ERDAP server won't be able to fulfill that request. So that's what GridApp initialize does. It runs in the background and it tells you what is available on this data set. So on this one, it's telling us that available variables are SST, error, mask, and C-ice fraction. We're going to go for SST. So we then have a bit of a mess around with this thing called constraints. So the constraints is how we control what server-side subsetting is done. So I'm telling it to do steps of 10 in latitude and steps of 10 in longitude. So we're kind of reducing the data by a factor of 100, which should make this all a bit quicker. And then I just run DS to Xarray. You can just run a pretty quick query against these. You don't have to spend a lot of time setting a query up. So that sends us back this data set. Xarray tells us it's 52 megs. Even subsetting in its steps of 10 in longitude and latitude, we still get back 3,600 long, 1,800 lat. Gives us the coordinates. Notice that it sent back only one value in time. And that's intentional. If you don't tell GridApp otherwise, it will just send you back the most recent time slice. So you can pretty much always just fire off a request to ERDAP and it'll give you back a manageable amount of data, which you can then use to plan your next step. So now I know kind of the size of this thing. I can just plot it up. So this is just a nice quick SST plot. This has already been subsampled by a factor of 10 longitude and latitude, and it already looks really nice. Sorry, let me just zoom out so you can see. That is just dot plot. I love Xarray so much. But now that we've seen kind of the shape of this, we can start to be a bit more specific. So I'm going to zoom in on the Gulf Stream and take a few time slices. So I get going again with my constraints. This time I'm giving it a time window. So I'm saying, all right, from 2023, start in January, go through to May, time step of 30. I already know from reading the metadata that this is a daily product. So this will give me approximately 1 data sample per month. I give it my little longitude and latitude window around the Gulf Stream. I know this time I've set the step to 1 rather than 10. So we'll no longer subsample in longitude and latitude. We'll get this stuff at maximum maximum resolution. So we've set our constraints, we've set our variable, and we run to Xarray again. So now we just do a little bit of extra specification with our Xarray plots. So I'm doing a slice in time. So I first plot it in January, and then the next slide, I'm plotting it in May. So you can kind of flick back between the two and see this changing structure of the Gulf Stream And I've just specified some extra vmin, vmax, and levels so that we get a consistent plot. But this is my general approach to Xarray. I'll make a quick request against the data set to see how big it is and like what the dimensions are. I'll do some kind of coarse subset while I get the hang of what I want, because I'm not running these notebooks live, but each of these requests is taking like 10 seconds, maybe up to a minute. So then once you know that you've got what you want with coarse data, then you can take the step down into a smaller step and get the full data set. It just means that you can kind of iterate on this stuff quicker if you start with a coarse set. There's this really nice topography set from the Hawaii ERDAP. A lot of these notebooks was me just trying to pull data from various different ERDAPs to give people some ideas. So this is a fun one to play around with. Just set some constraints, put it to Xarray, and then, yeah, you can make your nice little kind of Jedco style plot with a bathymetric map. Notice that Xarray also takes cartopy projection keywords. This is us setting up matplotlib with cartopy projection keywords. So you can mess around with that and make some more interesting plots. But that's kind of the magic of GridApp. As I said, you just need to make sure that you run, I don't know, I have it all on that last slide. Sorry. You just need to make sure that you run this GridApp initialize after setting your dataset ID so that it can talk to ERDAP and get your constraints. You can then be more specific with your constraints, pull it all to Xarray and get to plotting. I think we're 2 minutes from the end, so I will wrap the screen share there and take any final questions.
So I have a question about so a lot of data is like moving to the cloud. And I don't know, I thought it might be good to mention some of those, like there's the Google has open data, AWS, the open data, and then the NASA and Copernicus data, which is not ERDAP, it's a different kind of server.
Yeah, so you talk about like S3 bucket storage and things that are running behind some of these cloud servers. Yeah.
I'm going to show that during my tutorial.
I was going to say, I hope someone's going to touch on that later, because that is, yeah, a really useful data source. So thank you for jumping in there, Rich. More of that will be covered later. I think yeah, please go.
I saw in the manual that ERDAP can do some server-side calculations, like create new variables. It's possible to do that while pointing to a thread server. Like you can create magnitudes from zonal and meridional components.
That is an excellent question. I don't know. I'm going to answer this late. I'm sort of hoping that Felipe is going to unmute himself and save me on that one.
Sorry, I'm muted mostly because it's very noisy here. I don't think that's possible with threads. You probably have to download the whole thing and do it locally. Reach is on site, right? Maybe Reach knows something, but as far as I know, threads cannot execute any code on the server side, only ERDAP.
Okay, thanks.
Nice. And I think that's us at time. So I will hand control back over to Kath, I think.